Unit 2C, Introduction to Statistics, the shape of a distribution. When a distribution of scores is graphed, we are often interested in the shape of the distribution. If we have a bar graph that's shaped like this, this particular graph is called symmetrical or balanced. If we drew a line down the middle, you'll notice this piece matches this piece. This bar matches this bar. The height of this bar is the same as the height of this bar, and so on. If we folded the graph along this central axis, one side would land exactly on the other side. They match up perfectly. This is called symmetrical distribution. If a distribution looks something like this, well, it too looks symmetric, but it also has a mound shape, so you'd say it's mound shape. Or we could say it has this kind of a shape. Shape like a bell. A bell looks like that. This is a bell-shaped distribution, or we're going to call it later on a normal distribution. If the bars look like this, this looks a little bit like what we just had, but you may say that this particular one looks like a triangle. It's also mound shaped, but this would be called a triangular distribution. If all the bars are the same height, they're of uniform height, then this is called a uniform distribution. If the bars are like this, this is not a symmetrical distribution, but if we think of the scores being down here and the frequencies being here, this score and this score have the highest frequencies. So they're both called modes. They would both be modes. So this particular distribution would have two modes, so it's called bimodal. It has two high points. It's going to have two modes. If we have a distribution let's say it's basically mound shaped like this, perhaps symmetric, and we add some more scores out here. then this is no longer symmetric. It's distorted, and it's distorted by having a long tail on this side. We say it's skewed. Skewed means distorted. It's skewed to the right because this tail is on the right side. We've added scores out here on the right side called outliers, and they skew the picture to the right. Of course, if the shape of the curve was like this, that would be skewed left. That's skewed left. This is skewed right. Here are some examples. This one is symmetric, and it's mound-shaped. Example B, all the bars are the same height. This is called uniform. Here we have a case where the distribution has scores out here on the left, so there's a left tail here. It's skewed to the left. Here we have a distribution where it's skewed to the right. In this case, we have these two scores would both be modes. This is a bimodal distribution. Is this distribution skewed right? Well, I think you should see that it's got a tail out here to the right. So yes, it is skewed to the right. This particular one, what percentage of the students had a grade of 70 or below? That's the question. This particular graph measures the grades the students got with their cumulative percents. These should actually be percents here. This should be 20%, 40%, 60%, 80%, 100%. Anyway, the cumulative percent, in other words, what this means, 6% of the students had a grade of 50 or below. 15% had a grade of 60 or below. And the question says, what percent had a grade of 70 or below? 70 or below would be 37%. So the answer would be 37%. By the way, this cumulative percent graph has the basic shape of the ogive. It's a cumulative percent, so it has the basic ogive shape. Here is a distribution where we have most of the scores in here, and then we have an extreme score out here. This is called an outlier. It's far away from the rest of the distribution. Also, you could consider these scores too as outliers. They are extreme scores. Here's an example of what they call a time series graph. We have time down here on the x-axis, and in this particular one, we're measuring over the years the river discharge from the Mississippi River. In 1955, it discharged 300 cubic kilometers of water, and the next year it went up, and so on. Anyway, you can see that this would be the polygon or the line graph of the discharge of the water. And then what we have here is what is called a trend line. If you notice, this graph is generally speaking going up as you go from left to right. So as you go from left to right, this line is going up. So we have a trend line, which is telling the person that the discharge from the river seems to be going up as time goes on. Here's an example where you could be a little bit deceptive with statistics. This shows the age of people, drivers, and the number of drivers that had fatal crashes in this particular year. And if you notice, the teenagers, 16 to 19, they had, and this is in thousands, they had 6,000 fatal accidents. The early 20 group, they had the most. They had about 9,000 fatal accidents. And look at the old people here. The old people, relatively few fatal accidents. So this says to the people that young people should not be driving. Young people are dangerous people. They're involved in fatal accidents. But if we look at the data in a different way, and we look at the age of the people compared with the number of crashes per 100 million miles driven. So if we compare the accidents with the number of miles people drive, then the teenagers would have a relatively high number of fatal deaths, 12.5 deaths for every 100 million miles they drive. And the 24-year-olds would also have a pretty high fatality level. And then the people in the middle don't seem to have such a high level. But then look at the end. These people that are over 75, they have the highest fatality rate per 100 miles driven. So what's going on here is that older people don't drive that much, but they have a relatively high number of accidents per mile. The younger people drive a lot, so it's natural that they would have more fatalities. So this indicates that the senior people are the dangerous people. Maybe more dangerous than the young, although the young is still pretty dangerous. Here's another deceptive chart. Suppose the average salary is $40,000 and for men and less for women. Well, when you first look at this, it looks like the women earn about half the amount that the men make. So you might think that women earn $20,000. Now this break in the vertical axis, this means that there's some scores that are missing. This does not necessarily represent the height of 0 or the salary of 0. So this picture could be deceptive. Maybe the truer picture would be this picture, where the height of men is 40,000, but the women are almost the same amount as men. Maybe they're 39,000 or something like that. So where did that other picture come from? The other picture came from the fact that we disregarded most of this axis, and we only looked at something like this amount right here. And then the blue bar would look like it's twice as high as the red bar. So you got to be careful. This particular picture is very accurate because it has the 0, and it has all the scores from 0 up to 40,000. If the 0 is not on the bottom, is not there, and there are scores missing, the picture could be deceptive. That's the end of Unit 2C.